This is no ordinary rocket engine. Limited by the technology of their times, engineers and physicists have theorized this propulsion method for centuries, but the constraints of time may have just lifted with NASA's revolutionary test of this rotating detonation engine in January 2023 with the very latest advances in material science and computational fluid dynamics. NASA has managed to break through to test a 3D printed rocket engine that could improve fuel efficiencies of rockets by up to 5%. A 5% improvement in efficiency for a rocket is not a marginal gain. Rocket weights are dominated by fuel. The first stage, Saturn V, had a dry mass of 137,000 kilograms when fully loaded with propellant. Its weight was 2.2 million kilograms. The first stage was 94% fuel. A 5% increase in fuel efficiency represents a 103-ton decrease in fuel. That's not far off the total dry mass of a Falcon 9 rocket. This does not just provide cost savings, it represents a drastic change in capabilities of rockets, allowing humans to launch larger payloads further into the solar system. This latest test of the technology saw the engine run 18 times with a maximum firing duration of 113 seconds per run. This was a test, and the engine is not ready to use, but this test represents the culmination of decades of research enabled by newly developed metals and manufacturing techniques and the very latest advances in computational fluid dynamic modeling. Let's delve into the science and engineering behind rotating detonation engines to see how they work. Engines powered by detonations are not a new concept. The Air Force Research Laboratory developed this highly modified Rautenlong EZ powered by 4 tubes in which the detonations occurred. Traditional rocket engines work by mixing fuel and oxidizer using a continuous igniter with the igniter typically located at the top of the combustion chamber. A flame front needs to travel through the fuel mixture to complete combustion. If the speed of this flame front is below supersonic speed, the combustion is called defloration. If the flame front travels through the mixture at over Mach 1, then the process is called detonation. Almost all combustion engines work with deflagrations, but as their name implies, rotating detonation engines use a supersonic flame front to produce thrust, and as a result can produce more thrust for the same volume of fuel. However, this is easier said than done. The energy needed to initiate a detonation is very large, and for these pulsed detonation engines used on the Air Force's test vehicle, the detonations needed to happen hundreds of times a second. We can initiate a normal deflagration combustion flame front, which travels through the tube and with some encouragement will transition to a detonation, but the causes of this are not totally understood and not always reliably repeatable. We know that detonations happen more often when the fuel is turbulent, so to create these conditions, pulse detonation engines often include a physical barrier. One method to achieve this is by placing a spiral inside the two. Pulse detonations have a more obvious problem: they don't provide constant thrust. They pulse. Rotating detonation engines are the solution to both of these problems. They consist of a ring-shaped combustion chamber. The process starts by opening a valve at one end of the tube and letting a fuel mixture fill the tube. The valve closes and an ignition source at the closed section goes off, and the detonation begins. A shock wave begins to travel around the circumference of the ring. This increases the pressure and temperature of the gas behind it almost instantly. This gas then expands and leaves the tube at extremely high velocity, creating thrust. This cycle then repeats with the shock wave traveling in a never-ending circle. This clever major problems OE chromium and copper